Hi everyone, my name is Satyaam Raha. Welcome back. So in the previous video, we have learned about how the training process in a neural network happens, right? So you got the idea what the mathematics is behind the training, right? So in this video, let us talk about a concept which is very important when it comes to the neural network. That is a concept called memoization. So see, why is it required? The first thing is, since you have seen in the last few videos, in a neural network we can have so many hidden layers, and obviously there will be a lot of neurons, right? So when we are back propagating, like when we are finding the derivatives, the partial derivatives of the loss with respect to any weight in any hidden layer. So what we did is we had to calculate so many derivatives, right? So many partial derivatives, because we use chain rule. We could not find it directly. So what we did is, if suppose I have two hidden layers, as for example in of the last neural network where we had the two hidden layers. So as just suppose we need to find out the derivative of the loss with respect to any weight in the first hidden layer. What we required is all the derivatives in between, right? Just by using the chain rule. So we needed to calculate the derivatives each time when we needed to find any partial derivative of the loss with the particular weight. So it is not very efficient, okay, because calculation of the derivative is a bit complex. It is time consuming. So can we do something about it? Okay, because there can be thousands of hidden layers, and there can be thousands of neurons as a result. So there will be weights with a huge dimension. There can be like n dimension weights, right? There can be thousands of weights, 1 lakh weights in a deep learning network. So what do you think? If you have to find the partial derivative of the loss with respect to each of these weights, you need to calculate all the derivatives that comes in between, right? I'll show you an example. Maybe it's getting confusing. Let us see with an example. I hope my screen is clear. You can see for this particular example which we had learned, we had used in the last videos. See, this is just a simple example of two hidden layers, right? There are two hidden layers over here. You can see only two hidden layers. In real life, we'll have a lots of hidden layers, right? And we'll have so many weights. You can see here we have so many weights. Here 4 cross 3, so 12 weights, right? 12 weights are present in this particular layer. Here we have 3 cross 2, that is 6 weights, and here we have 2 cross 1, that is 2 weights. Okay, so in this simple neural network we have like 3 to 12 and 6 18 and to 20 weights that is to be computed continuously in each epoch, right? So we had to find something like this. Say for example, we had to find the derivative of L, partial derivative of L with respect to this 3 1, for example, right? Which weight am I talking about here? Which weight am I talking about here? Just understand, this is W3, right? This is W3, and here you can see over here, if I have to find this particular, this is not just let me change it to something which is let's say, okay, let me write the weights first. Let's say this is the weight W3, and this is coming from the first neuron and going to the first neuron, right? Here it will be W3. Let me calculate it. This is the second neuron, and here it is the first neuron. So 2 1, right? Let me write for this one W2. This is coming from the first and going to the first, W2 1 1. Okay, so I'm not writing all the weights. You know the convention, you know the notation. I'll not be writing it here. It will be very messy. So just see, for example, if I have to find this particular partial derivative, what we needed to find out something like this: loss with respect to this, right? And this with respect to, if I have to find out for, let's say, W311, that means this weight, right? This is dependent on this. So I had to write like this: 31 by this is nothing but W311. Yes. Again, just see, if I have to find out with this particular weight, so partial derivative, if I have to find out for this, you can see, sorry, not 31, it will be output 21, then output 21 with respect to this weight, isn't it? So you can see over here something that is just a second, here I have written it mistakenly, it's not 21, it will be 31, right? Yes, you can check it here. So this loss is dependent on O31, and this O31 is dependent on this weight as well as this weight. So you can see here, for this simple neural network, I had to calculate this thing twice, just for updating this particular layer, just for updating weights in this particular layer. Now you can imagine, if I have to update the weights of this particular layer, what will happen? What will happen? Just tell me. So I have to recalculate it again and again, this particular derivatives, obviously, because it will go from this is the path, right? This is the path. So I have to calculate every time. I'll just show you. See, let me do it here with a different color. Let's say I have to find out derivative of L with respect to derivative of W211. Tell me what will be the chain rule here. So this loss is dependent on O31, so I'll write it like this: is dependent on O31, and this O31 is dependent on, you can see here, O21. We did it in the last video. If you were confused, you can check the last video, it will be very clear. From O21 is dependent on this, right? So O21 is dependent on W211. So you can see here also I have to calculate this particular thing. This is same thing, right? It is repeating. So for all these layers, for all these weights, I have to recalculate this particular derivative. This is just an example, okay? There will be lots of such derivatives which has to be recalculated again and again. And obviously, calculating this derivative is not very easy, right? This is not some kind of addition, not some kind of subtraction. It is derivative, okay? So we have to find it again and again. We have to calculate it again and again, and it will take a lot of time. And you can imagine, for a like 1000 hidden layer model, it will be very much time taking. So what we can do about it? So the solution is something from the concept of dynamic programming. Okay, all those who are aware of the subject data structure and algorithms, I think you came across a concept called dynamic programming, which is very much used in competitive programming. Okay, so similarly here, this concept of memoization, it is not memorization, okay, it is memoization. Memoization is nothing but a concept of dynamic programming from data structure and algorithms. Okay, what it does, I'll just show you what it does. Let me just erase this. I'll show you what it does. Okay, let me take a different color. Okay. Okay, since we have to calculate this particular thing over and over again, why not save it once and use it multiple times. So what we can do is we can simply store the value of 031, this value. Why not store it in this particular node? Right? You can imagine these neurons as nodes. So why not store this particular information, and it could be reused again and again whenever we need this value, because every calculation over here will go through this path. So why not? First you have to calculate it once, okay? That cannot be like avoided. That must be done. But what we can do is we can calculate it once and store it somewhere, just like dictionaries in Python, okay? Dynamic programming concept, we can save it as a dictionary of, let's say, F31, or we can save it like loss with respect to 031. The value once calculated, let's store it here. Then we can use it multiple times. Whenever we need it, we'll calculate for this time, and we'll reuse it here. We'll reuse it here. Okay. Similarly, what we can do is we can store here some value called 031 with respect to 021, right? We can store this value over in this node. Here what we can do, we can store the value of 031 with respect to 021, and we can reuse it multiple times. Here what we have to do, see, this is the two path, right? From the last video you remember, I guess, there is two path. One is this path, another is this path. So we have to calculate two derivatives, okay? One is the 2-1, see, from this 2-1 is dependent on this particular weight, right? So 2-1 with respect to 011, yes, this 2-1 is dependent on 011. Also here we have to save another derivative, which is this path. So derivative of 022 with respect to 011. Yes, if you remember from the last video, we calculated these two derivatives, right, in the chain rule. So we can save these two values in this particular node, and we can reuse it. Here also you can see we have to save two values. So 022. So here also two paths, right? If we take this path, so it is 2-1. So 2-1 with respect to 013. Also we can save another value, which is this path. So 022 with respect to 013. Yes, we can store it in this particular node. We don't need to store this because we have already stored it here. So we can already fetch it from here, right? Okay. So if we save it like this, in this particular nodes, what we can do is we can reduce the time very efficiently, right? So that is why memoization actually changed the scenario. It made the deep learning much faster. Okay, so I hope you understood the concept. What I will suggest is I will maybe show you this entire thing hands-on in Python. Okay, I'll show you how it works. Let me first complete a few things like backpropagation first. Then I will show you the entire hands-on of this whatever I have taught till now. After I have taught the concept of backpropagation, I'll show you hands-on in Python. Okay, I'll show you how the entire things can be implemented in Python very easily. Okay, so I hope you understood this concept. If you have any doubt till now, so please try to implement it as a Python code or whatever language you feel like. In Python it will be very easy to implement. Okay, otherwise you can wait till I show it as a video. Okay, so thank you for watching. See you in the next video. Thank you.